All right, welcome to Physics Video 6.4. We are going to learn today about work done by non-conservative forces. So objectives, by the end of the video, you should be able to do these three things. You should understand the connection between the work done by a non-conservative force and the object's total energy. You should be able to calculate work using two different methods, which will both be outlined here. And thirdly, you should be able to use the work and energy to find an object's height or velocity at a specific instant, similar to how we did when we did conservation of energy in the last video. Okay, so before I do, I guess I should reiterate and remind you, if you've not yet done this, you need to be making the connection between velocity and kinetic energy and height and gravitational potential energy. That is crucial that you understand that. Okay. Also, as a reminder, remember that when work is done by a non-conservative force, it changes the total energy of an object, which I think the video says that here. So here we go. Law of conservation of energy. This is the same as was in the last video. Energy cannot be created or destroyed. It can only be converted from one form to another or passed from one object to another. So what that means is, as long as energy is not passed from one object to another, in other words, if the non-conservative forces don't do work, then an object's total energy will always remain constant. That's what we learned in the last video. If the non-conservative forces don't do work, then an object's total energy will always remain constant. Okay. So today we're going to learn about what happens if the non-conservative forces do work. Okay. So once again, energy cannot be created or destroyed. Energy can only be converted from one form to another or passed from one object to another. All right. When a non-conservative force does work, that's what's happening. Energy is passed from one object to another. The object doing the work usually gives the other object energy. Okay. And so this part down here is the premise behind this video today. All right. The work done by all the non-conservative forces on an object equals the change in the object's total energy. That is hugely important and is the whole idea behind work. Remember, work causes energy to change. Okay? Total energy is GPE plus KE. And what I told you before was anytime work is done by any force, one of these three things changes, at least one of those three things. Okay? Now we're being specific. Work done by a non-conservative force will cause this total energy to change. Okay? And as a result, since the total energy is changing, that means that at least one of these guys has to change too, right? Okay? Which brings us to our first new equation of the day. Which says the work done by non-conservative forces is equal to how much the total energy changes. It's the difference between how much you ended up with subtracted and then subtract what you started with. All right? Another way of thinking about it is this. The total energy that you're going to end up with is however much you started with plus however much you gained from that outside force, that non-conservative force doing work on it. Okay? So to better understand that, let's do a real quick example here. Okay? So in this example, it says Roy lifts a 5-kilogram box of papers. That'd be a big box of papers, from the top of the desk, which is 0.8 meters tall, and places it onto a shelf that's 1.5 meters above the floor. And it wants to know how much work did he do. So same as last video, make a drawing. Okay, so whatever. Here's the wall with the desk on it and the shelf. Here's our box of papers that we're interested in. Okay, so that's our starting point. And then he's going to lift it up to here, right? So, just like always, we want to think in terms of height and velocity, and you need to think about specific points in the object's motion. In this problem, there are 2 points in the object's motion that we care about. There's what's happening when it's on the desk. So what's happening when it's on the desk? Well, we know the height is 0.8 meters. And presumably the papers were just sitting there. I should have said that in the problem, but we can assume the velocity was 0. Okay, so that's one thing. Then at the top, he's lifted it up onto the shelf. And so now the height is bigger. Now the height is 1.5 meters, but he's placed it onto the shelf. He's going to be sitting there at rest again. The velocity is 0. Okay, so that's the information we know. Oh, in addition, we know the mass of the box, right? It's 5 kilograms. So mass is 5 kilograms. Okay. So remember, work is the change in total energy. So we need to find the total energy. So to do that, what I'm going to do is find the total energy initial. This is going to be my initial point, right? And this is my final point up here on the shelf. So GPE equals mass times acceleration of gravity times height. I should be able to find out my GPE. The mass is 5, times 10 is 50, times 0.8 is 40 joules of gravitational potential energy. Since the velocity is 0, the KE is 0, which means my total energy initially, the total energy that my box began with before Roy lifted it, is 40 joules. Okay? Now he lifts it up. So we're going to go through the same process again to find our total energy final. So GPE is mass times acceleration of gravity times height. So the mass is 5 kilograms, times 10 is 50, times 1.5 is 75 joules. The box, once again, is not moving, so the kinetic energy is going to be 0. Notice the box does move in the middle, but Roy does a little bit of work to get it moving, and then this is being a little sloppy, but basically he has to stop it again. So the kinetic energy, he gives the box kinetic energy, but then takes it away again. So it starts and ends at 0, which is what we're worried about here, is what you start and end with. Okay? So the total energy that the box ends with is the 75 joules of GPE plus 0 gives you 75 joules. Okay? So check it out. In the whole last video, we kept saying that our total energy is constant, that the amount of energy that you begin with is the same as the amount that you end up with. But now that's not the case because there was a non-conservative force, right? Specifically, Roy. Roy is a non-conservative force here, right? Because he is exerting a force. He's not gravity, and he's exerting a force in the direction of motion, right? So, because of that, our total energy has changed. Here's the results of it. The total energy went from 40 up to 75. So now we can go back and find our work. To find the work done, we find the change in total energy. So for this example, I'm going to write it on the screen where there's some room. You know what? We can go back to the other screen. So, oh my gosh, sorry. So to find our work, the work done by non-conservative forces, the work done by Roy, is the change in total energy. So the work done by Roy, because he's our non-conservative force, the work done by Roy is 75 joules, what we ended up with, minus 40 joules, what we began with, and you get 35 joules. That's how much work Roy did. It's also how much energy he gave the box. That's worth writing down. That's the work done by Roy. That's the same as how much energy he gave the box. Okay? And notice the question said, how much work did he do? All right? So there we go. So, check it out. In this problem, I keep saying check it out today. I'm not sure why that is. In this problem, Roy was exerting a force. That's what did the work. And it seems like there should be a connection between how much force Roy exerts and how much work he does. And it turns out there is. Okay? Work is done by force. And so it turns out another way to find the work is to take the amount of force exerted, to find the work done by your non-conservative force, you take the amount of force exerted and multiply it by the distance that that force acts over. Technically, it's the displacement. I probably should have written triangle X there, but most books use a D. So this looks a little bit weird, so let me rewrite this so it's not typed. In that last example, we could say that the work done by Roy was equal to the force that Roy exerted times the distance that he exerted that force over. So let's do this. I hadn't even planned on doing this when I made this video, or when I made this sheet, but check it out. In that last example, here's what we know. We know the work done by Roy was 35 joules. That's got to equal the force that Roy exerted, which I didn't give you, times the distance he exerted the force over. Well, let's go back for a second and check it out and see if we can figure this out. The distance he lifted it, let's see. He lifted it from a height of 0.8 meters up to a point of 1.5 meters, right? So the distance would be the difference between those two things, wouldn't it? So 1.5 minus 0.8 means that the distance that he exerted the force over to lift it was 0.7 meters, right? The difference between 1.5 and 0.8. Okay, so 0.7 meters. And now you can divide both sides by 0.7 meters to find his force. And so you find out that the force of Roy is 35 divided by 0.7 gives you 50 newtons. Okay, so now I know how much force Roy used to lift the box. Cool. If you care, which some of you do, some of you don't, that happens to be the same as the weight of the box, right? 5 kilograms times -10, or times 10 meters a second squared to find the weight, the force of gravity, gives you 50 newtons. So, all right, there we go. So I want to do another example using this equation. I got a little sidetracked here by exploring that last example. So let's explore this a little bit more. The work done by a non-conservative force is equal to that non-conservative force times the distance. So here's another simple example. It says a cart with a mass of 40 kilograms is pushed from rest 12 meters across a horizontal floor with a force of 50 newtons. Find the final velocity of the cart. Okay, so make your drawing. Here's your cart. Let's say it's a shopping cart. Okay, and it's going to be pushed this way, a distance of 12 meters to another point, right? So here's what we know. We know the mass is 40 kilograms. It says it's being pushed from rest, so that means the velocity over here is 0. It doesn't say what's pushing it, so let's assume it's Roy again. So here's our force of Roy, 50 newtons. And so we're trying to find the final velocity of the cart, so we're trying to find the velocity over here, right? So, this is tricky. We got to think in terms of energy, right? So we're going to do a couple things. First of all, let's analyze the energy, okay? So let's do this. Let's call this our initial point, and we're going to call this our final point. So over here at our initial point, we know the velocity is 0, which means that the kinetic energy is going to be 0, right? In this problem, it doesn't look like the height is even an issue, so I'm just going to say the height must be 0. It's being pushed horizontally. It's not going up or down at all. So that means the GPE is also 0, which means that my total energy that I began with initially was 0. Now, Roy is a non-conservative force, right? And he's doing work because his force and the velocity are not perpendicular, right? So we don't know the total energy final. All right, so we do know over here the height is still 0 though, so the GPE is still 0. We don't know the kinetic energy because it's moving, right? We just don't know how fast it's moving. All right, so there's some information I haven't used yet, and specifically that's this. Remember, oops, I tried to change colors there. We know that because there's a force pushing the box some distance, work is done. So let's find our work. Work is, in this case, the work done by Roy is equal to the force of Roy times the distance he pushed it. So his force is 50 newtons. The distance he pushed it is 12 meters. Multiply that and you get 600 joules. You can do unit analysis on that and verify that it comes out to joules, but it does. Okay? So that's how much work Roy did, 600 joules. All right? Now remember, you guys, work is the difference between the final energy and the initial energy, right? Or, I think I also wrote it this way, the total energy you end up with is whatever you started with plus the work that was done. Oh, I'm sorry, I forgot my little NCs for non-conservative. Okay, so at this point, you're probably getting a little bit overwhelmed, but here's the deal. Look, the total energy is not staying the same because Roy did work. Work represents how much energy Roy gave the box. So The box started out with, no energy, and then Roy did 600 joules of work. So the total energy final is what we started with, 0, plus the 600 joules of work that Roy did. So my total energy final has to be 600 joules, right? Okay, and so now that we know that, now we're back to what we were doing in the previous video. If the total energy is 600 and the GPE is 0, then the KE must be 600 joules. And finally, we can use that kinetic energy to find our velocity. So it's 2 times 600 joules divided by the mass, which was what, 40 kilograms? Square rootify it, and you get the square root of 30, which is some number. It turns out to be about 5.5 meters a second. Oh no. All right, so this problem kind of ties everything together, right? We had to use force times distance to find the work done by Roy. And then we had to connect that to our change in energy. We started out with no energy. Because Roy did 600 joules of work, we gained 600 joules of energy. Okay? So let's do one last example here. I'll try to squeeze it in the 4 minutes to keep it under 20. So here we go. Little Sally has a mass of 20 kilograms. She climbs to the top of a slide that's 3 meters tall, sits at rest at the top, and then slides down the slide, which is 6 meters long. Find her velocity when she gets to the bottom, 0.75 meters above the ground, if friction exerts a force of 25 newtons as she slides down. Pause it and try this first. Okay, I'm going to assume you did that. And here we go. Let's draw it. We need a slide, right? Slide looks like a ramp. Doesn't quite go down to the ground, right? Okay, so here's what we know. We know that when she's at the top of the slide, her height is 3 meters. She sits at rest at the top, so the velocity at the top is 0. The question wants to know when she gets to the bottom, what's her velocity if the bottom of that slide is 0.75 meters up. Other information that we've got is Sally's mass, which is a measly 20 kilograms. So here she is. Hello, very small baby Sally. Bloop, bloop, bloop. Okay, and the length of the slide, the distance that she's going to slide is 6 meters. Okay. Oh, we also know friction, right? Friction, as she goes down the slide, I should have drawn her actually on the slide, is going to exert a force of 25 newtons, right? So she's going to slide this way, friction is this way, so one of those needs to be negative, either the 25 or the 6 needs to be negative, depending on how you want to think about it. Okay, so we're going to solve this the same way we always do. If we know the height, find the GPE. If we know the velocity, find the KE. So here we go. I'm going to do this pretty quick. Oops. So up at the top, I know that my GPE is mass times 10 times height, so 600 joules. She's at rest, so the kinetic energy is 0, which means my total energy at the top, total energy initially, is 600 joules. Down at the bottom, my GPE is mass times 10 is 200 times 3/4 is 150 joules. Now, I don't know the kinetic energy, and because there's friction, which is a non-conservative force doing work, I also don't know my total energy because it's going to change. So let's find the work. I can't find work by doing the difference between the energies because I don't know it. So I'm going to find my work by doing force times distance. So work done by friction, right, is going to be the force of friction, 25 newtons, times the distance, 6 meters, and it's going to give me 150 joules. Oh, that's frustrating that those both came out to 150. It's just coincidence that this is 150 and GPE is 150. That is a weird coincidence. All right. Now remember, our work is negative because either the force of friction or the distance has to be negative. Again, it doesn't really matter which one, but one of them needs to be negative. Okay, so what this is telling me, this number, write this down, you guys, this number, this work is telling me that friction caused Sally to lose, because of the negative sign, 150 joules of energy. So my total energy final is going to be the 600 joules that we started with minus the 150 joules we lost because of friction. So the total energy final is going to be 450 joules. And now that I know that, I can find my kinetic energy, right? 150 plus something is 450. So the kinetic energy has got to be 300 joules, which I can now use to find her velocity. So 600 divided by 20 is 30. Oh, wow, you get the same thing you got in the last problem. Weird coincidence. All right, so there you go, 5.5 meters a second. All right. Maybe I should take a second to write the numbers. 2 seconds, girls. So that the kinetic energy I used here is 300 joules. Okay, cool. Happy videoing. Where's my pause button?